Chapter 7.4 Reciprocal Functions. Example, compare y equals x and its reciprocal function using a table of values and a graph. We've heard of reciprocals before. When we divide by a fraction, we multiply by the reciprocal of that fraction, which is to say that we flip the fraction upside down and then multiply. If we have a function, the reciprocal function is just 1 over that function. Let's fill in the table of values for the function y equals f of x. So we have the x values in the left column, and then it would be the y values in the middle column. In this case, y equals to x, so it's just going to be same as our x values, -3, -2, -1, 0, 1, 2, and 3. Let's plot these points for f of x on the grid. When x is 0, y is 0, x is 1, y is 1, x is 2, y is 2, etc. Draw a line. Now let's fill in the table for the reciprocal function 1 over f of x, which in this case, because it's just y equals x as our function, it would just be 1 over the x value, which is -1 over 3, -1 over 2, -1 over 1, which equals -1. When x is 0, we can't divide by 0, so that value is undefined. X is 1, we get 1 over 1, which is 1. X is 2, we get 1/2. And x is 3, we get 1/3. Let's plot these points on our grid. When x is -3, y is -1/3. I'll say that's about there. When x is -2, y is -1/2. When x is -1, y is -1. And then at x equals to 0, the graph is undefined, the function's undefined, so there's no points on the graph at x equals 0. When x is 1, y is equal to 1. When x is 2, y is equal to 1/2. And when x is 3, y is equal to 1/3. We can use our graphing calculators to help us get an idea of what this is going to look like. Y equals, clear what you have. We have 1 over x. Graph that. I'm going to set my window to standard. And I get this. This is what the reciprocal of a linear function looks like. So we have two curves. The blue line that goes up x equals to 0, that is called the asymptote. So we talk about asymptotes down here a little bit. An asymptote is a line that a curve approaches but never reaches. You can have vertical asymptotes where x equals a number, or horizontal asymptotes where y equals a number. So when you graph in your graphing calculator, it kind of looks like there's a curve, and then it attaches to a line, and then it attaches to a curve. So kind of thinking like heartbeat, that's what it reminds me of. A heartbeat on a monitor that you've probably seen on like medical TV shows. But in reality, they're not connected. So there's just two parts. There's the one curve, and there's this other curve, okay? So even though it looks like they're connected with this line in the middle, they're actually not. That's just the graphing calculator showing us the vertical asymptote. So because we said that our reciprocal function is undefined at x equal to 0, that's our NPV. And when we're graphing rational functions, that's going to turn into our vertical asymptote. Okay, so we have a vertical asymptote at x equals to 0, which is just the y-axis. And then we have these two curves, one in the top right and one in the bottom left. So they get really, really close to the x-axis. They curve around through these points that we have, and then it gets really, really close to the y-axis, but they never actually touch either axes. And then same with the top left or top right side. Gets really close to the x-axis, y-axis, sorry, and then it gets really close to the x-axis, but it's never actually going to touch. It's going to get very, very, very close, go through those points, and then get very, very, very close over here as well. So that's what our reciprocal function looks like, is the two blue parts. Now let's talk about the points that are the same. So we see we have these 2 points, and those 2 points are the same on both graphs. Those are called invariant points. Any points where the point is the same on the original function and on the reciprocal function is called an invariant point. And those occur here when x equals to -1 and y equals to -1, and when x equals to 1 and y equals to 1. And if we think about our two functions, we have our x value, which we sub into the function to calculate the y value, which is called f of x. The reciprocal function is 1 over f of x. So that also means 1 over the y value. Well, when y is equal to +1, 1 over y would equal to +1 as well. That was the situation down here. Y equals to 1, 1 divided by 1 is 1. And when y equals to -1, 1 divided by -1 is -1. So those values are always going to be the same. Then that tells us that our invariant points always occur when y equals 1 and y equals -1. And those will be the only invariant points, because any other value of y, 1 over that value would give us a different value. Okay, let's look at some more information. We have this table here. Where is the function undefined? So we're looking in this column at the original function, f of x, so just y equals to x. Where is the function undefined? Nowhere. There's nowhere that the function is undefined. For 1 over f of x, where is the function undefined? Well, that happened at x equals 0. It was undefined. So at x equals to 0. The next thing, state the behavior as x approaches infinity. So as x approaches infinity, x approaching infinity would be going this way. So what's happening to the original function, which is our linear, as we continue moving to the right? As we move to the right, this line here is going to continue moving up and right. So what's it going to do as x goes to infinity? Y is also going to go to infinity. Next one, state the behavior as x approaches -infinity. So we'll continue looking at the original function for now. As x continues going this direction, this line is going to continue to go down and to the right. So as x goes to -infinity, y is also going to go to -infinity. Now let's look at that same thing for the reciprocal function. as we continue going this way with our x direction, what's happening with this curve, it is getting closer and closer to y equals 0. So as x is approaching infinity, y is approaching 0. And then looking the other direction, as x is approaching negative infinity, what's happening with this curve, it's approaching 0 as well for the y value. The intersection points, we already said this, those were our invariant points. The two graphs intersect at -1, -1, and at 1, 1. State the behavior as x approaches 0 from the left. So looking at the original function first, from the left-hand side, approaching to 0. So x equals 0 is here. As we approach that, what is the y value approaching? In this case, the y value is also approaching 0. And then state the behavior as x approaches 0 from the right-hand side. Looking at our original function, as x approaches 0, which is here, y is also approaching 0. Then for the reciprocal function, as x approaches 0 from the left, so we're approaching here, what's our graph doing? Well, it's shooting down, very far down. So as x approaches 0 from the left, y is approaching negative infinity. And then last part, as x approaches 0 from the right, what is our curve doing? It is shooting very far up, so y would be approaching positive infinity. So this part here actually tells us that we have a horizontal asymptote at y equals to 0. And we can see that on our graph because our two curves get really close to y equals to 0, but they don't touch or intersect that line. Determine the reciprocal function for f of x equals 3x minus 9. As soon as we see reciprocal function, we need to think 1 over f of x. Our function in this case is 3x minus 9. So our reciprocal function would be y equals 1 over 3x minus 9. We can factor the bottom, so we could write this as y equals 1 over 3 times x minus 3. What are our NPVs for this function? Well, our NPV would be when x minus 3 equals 0, which would be when x equals 3. So that becomes a vertical asymptote for the reciprocal function. Graph f of x and its reciprocal, label any intersection points. F of x equals 3x minus 9 has slope 3, which is the same as 3 over 1, and a y-intercept at -9. So plot the y-intercept, -9, 3 over 1, up 3, right 1, up 3, right 1, put a dot, up 3, right 1, up 3, right 1, up 3, right 1, up 3, right 1, up 3, right 1. Draw a line. Then let's draw the reciprocal function. We know that it has a vertical asymptote at x equals to 3. So we draw a dotted line at x equals to 3. Wherever your original function has an x-intercept, there's going to be a vertical asymptote for the reciprocal function. So in this case, the only x-intercept is at x equals 3. that's our one vertical asymptote here. We're also going to have a horizontal asymptote at y equals to 0. So below it says find the equation of any vertical or horizontal asymptotes of the reciprocal. Our vertical asymptote is x equals 3, which is the NPV of the reciprocal, also the x-intercept of f of x, the original function, and then horizontal asymptote is y equals to 0. Y equals 0 is always the horizontal asymptote for reciprocals in Math 20-1. We'll see horizontal asymptotes at different values in Math 30-1, but in 20, you're always going to have a horizontal asymptote at y equals to 0. So we have that part. Now let's graph our curves. It's a linear, the original function f of x is linear. So our reciprocal function is going to look like the first one we did, where it has two curves, and they're going to be diagonal from each other. Let's plot some points. I'm going to make a table of values to help me plot some points. Okay, so I know that at x is 0, y is -9. So 1 over f of x would be -1/9. When x is 1, y is -6. So 1 over f of x would be -1/6. When x is 2, y is -3. So 1 over f of x would be -1/3. When x is 3, y is 0. So 1 over f of x would be undefined. When x is 4, our y value is 3. So we would have 1 over 3 for 1 over f of x. When x is 5, our y value is 6, which gives us 1 over 6 for f of x, 1 over f of x. And then when x is 6, y is 9, so 1 over f of x is 1 over 9. Let's plot those points for the 1 over f of x. So at x equals to 0, y is -1 over 9, which is really, really close to y equals 0, but just below it. And then when x equals 1, y is -1 over 6, which is just a little bit further down from that last point. When x equals 2, we have -1 over 3. And then when x is 3, it's undefined, that's our asymptote. When x is 4, we have +1/3. When x is 5, we have +1/6, and when x is 6, we have +1/9. So as we go to the right, our dots are getting closer and closer to the x-axis. And as we go to the left, same thing, our dots are getting closer and closer to the x-axis. So our curves should look something like this. With my pen here, so something like this on that side and like this. So it goes through those 3 points, gets really close to the horizontal asymptote goes through our 3 points, gets really close to the vertical asymptote. On the right side, gets really close to the vertical asymptote, goes through those 3 points, gets really close to the horizontal asymptote. There's our 2 curves. We also know we have invariant points. Which always happens when y equals to 1 and y equals to -1. Let's solve for the x values. If y equals 1, we put 1 equals 1 over 3x minus 9. We want to multiply both sides by 3x minus 9. We get 3x minus 9 times 1, which is just 3x minus 9, equals to 1. We add 9 to both sides, and we get 3x equals 10, and then we divide by 3, and we get x equals 10 over 3, which as a decimal divided by 3 is 3.33. Do the same for -1. -1 equals 1 over 3x minus 9. Multiply both sides by 3x minus 9. This time it does have an effect, so -1 times 3x minus 9 equals 1. Multiply the negative into the brackets. -3x plus 9 equals 1. Can subtract 9 from both sides. We get -3x equals -8, and then divide by -3. X equals -8 divided by -3, so 8 divided by 3 is 2.66. Repeating. So then our invariant points are when x is 3.33, y is 1, and then at 2.66 and -1. Discuss the behavior of the reciprocal as it nears the asymptotes. Let's look at the vertical asymptote first. Our vertical asymptote is x equals to 3. So the behavior of the reciprocal from the left side, so approaching x equals 3 this direction, our curve comes like this, and then it drops straight down basically. So it is heading towards -infinity there. As x approaches 3 from the left, y approaches -infinity. Can we guess what will happen as x approaches 3 from the right? So we're heading in towards 3 this direction. Our curve goes pretty much straight up, so it's heading towards +infinity as x approaches 3 from the right, y approaches infinity. Now the horizontal asymptote. And this is really usually called the end behavior. Okay, we pretty much talk about things in terms of when x is doing this, what's happening to y. So the end behavior means as x is getting larger and larger, so approaching infinity, what's happening to y, and then as x is approaching -infinity, what's happening to y. Let's take a look. As x gets larger and larger, heading out this way, our curve is Heading straight out, it's approaching the horizontal asymptote, which was y equals to 0. As x approaches infinity, y approaches 0. Then as x approaches negative infinity, our curve is right alongside our horizontal asymptote. So again, as x approaches negative infinity, y approaches 0. Let's also just take a look at the domain and range here. We'll do the function y equals 3x minus 9, and then y equals 1 over 3x minus 9. Domain for our original function, it's a linear, there's no asymptotes, so it's xer, x such that xer. Same with the range value, it continues forever up and forever down, so y such that yer. Looking at a reciprocal function, the domain, what x values are valid for this function? There's only one that's undefined, which is when x is equal to 3. So we get x such that xer, comma, x cannot equal 3. So everything except for 3 is what it's saying. And then the range, is there any y value that's undefined? Yes, we have a horizontal asymptote at y equals to 0. So y such that yer, y cannot equal to 0. All values except for 0. Determine the reciprocal function of f of x equals x squared plus x minus 6. As I said before, as soon as you see reciprocal function, you should think 1 over f of x. Our function in this case is x squared plus x minus 6. Our reciprocal function is then 1 over x squared plus x minus 6. Let's factor that. Two numbers that multiply to negative 6 and add to positive 1. That would be x plus 3, x minus 2. Now we can see what are our NPVs. Well, x plus 3 times x minus 2. When is that equal to 0? For this part, it's when x is negative 3. And for the x minus 2, it's when x is equal to 2. And with reciprocal functions, when we're graphing, our NPVs give us our vertical asymptotes. This one has 2 vertical asymptotes. Next part, what are the x and y intercepts of the reciprocal? For x-intercepts, the value of y equals 0, so set y equal to 0. We have 0 equals 1 over x plus 3, x minus 2. The only way to get a fraction to equal 0 is if the top equals 0. And there's no variable on top, so the value is 1 and it can't be changed no matter what the value of x. So this is just not possible. Which then means that there is no x-intercept. Let's do the y-intercept. We want to set x equal to 0 because the value of x at the y-intercept is 0. Y equals 1 over 0 plus 3 times 0 minus 2 is 1 over 3 times negative 2, which is negative 6. So y is equal to negative 6 is our y-intercept, and we had no x-intercept. Graph f of x and its reciprocal, label any intersection points. F of x is a quadratic function. It has x-intercepts at negative 3 and 2, because the x-intercepts of f of x would be the same as the NPVs for 1 over f of x. Negative 3 and positive 2. We can use our graphing calculator. X squared plus x minus 6 graph. Here's what it looks like. Second trace, let's find the minimum value, number 3, left of the minimum point, right of the minimum point, and it tells me it is x equals negative 0.5 and y is negative 6, about there, 2, 4, negative 6-ish. About there. And then our y-intercept for the original function would be negative 6, the constant value. So we can draw our graph. It's going to look something like that. Now let's plot our horizontal asymptotes for the reciprocal function. They go through the x-intercepts of the original function, which we saw here are x equals negative 3 and x equals 2 are the vertical asymptotes. I can use my graphing calculator to help me. 1 divided by bracket x squared plus x minus 6, close bracket. And we get this. So again, it looks like a heartbeat. The graphing calculators do not do a great job of helping you to graph reciprocals because it kind of looks like it stops at this point here. Where I can't even get on the point, but kind of looks like it stops, that red line stops at like negative 1, 2, 3, 4, negative 4 for the y value, but it doesn't. That continues down just like it looks like on the right hand side over here. It should continue the same way, and then same with going up this line here, that should continue upward. So using your graphing calculator for reciprocals is not the best. You kind of just have to understand how they work. So when we're graphing the reciprocal of a quadratic function, and our quadratic function crosses the x-axis, so it has 2 x-intercepts like we have here, then we're going to see our reciprocal will have 2 vertical asymptotes as we've drawn. Also, the vertex of our original function, our quadratic function, is between the 2 vertical asymptotes, which makes sense because it's between our 2 x-intercepts. When we graph the reciprocal of the quadratic, we're going to end up with a part between the 2 x-intercepts that kind of looks like a quadratic. It's going to open the opposite direction that our f of x function is opening, and it's going to be kind of wide and flat at the top like this. The 2 arms that are left and right of the x-intercepts on the original function, on the reciprocal function, those are going to become curves similar to the curves we saw on reciprocals of linear functions. They're going to look something like this and this. So altogether, when we have a quadratic with two x-intercepts, a reciprocal will look something like this. It's going to have a curve like that. It's going to have a sort of quadratic key thingy looking like that, and another curve like this. So that is about what our reciprocal will look like for these types of quadratics. Let's plot some points to help us draw the reciprocal. Reciprocal just means take the y value of the original function and put 1 over that value. So we can do that. Let's make a table here so we can plot some points. Let's start with the y-intercept. We know that the x value is 0. The y-intercept on our original function is -6. So -1 over 6 is the point that's going to be on our reciprocal. So x equals to 0 and y equals to -1 over 6, which is just below the x-axis. It's a negative number that's really close to 0. So we have that point there. We can look at the vertex. I forget what our vertex was already. Let's go back to graph, find our vertex, second trace, number 3, left bound, enter, right bound, enter. And so it was x is -0.5 and y is -6.25. So our reciprocal will be -1 over 6.25, which if I go back to my calculating screen, -1 over 6.25 is -0.16. So again, a number really close to -0.16, really close to 0, but just on the negative side. So at x equals to -1/2, y is equal to -0.16. Because that was the reciprocal of the vertex, then we would also have a point that would be symmetrical. So at x equals to 1, since we had x equals to 0, and then x equals to -0.5, and then x equals to 1, 0 and 1 would be symmetrical. We would have a point at the original function would be the same as the y-intercept, which was -6. And on our reciprocal function, it would be -1 over 6. Let's just find the decimal value of that. -0.1666. Okay, so a little bit lower than that -0.5 point. The other points that are really important and will help us to graph the reciprocal function are the invariant points, which occur when y is equal to 1 and when y is equal to -1. So where's y equal to 1? We have y equals 1 here and y equals -1 here. How many points do we have on our quadratic function where y is equal to 1? We have one that's just left of the vertical asymptote x equals -3. And we have one that's just right of the vertical asymptote x equals 2. How many points on our quadratic have y values of -1? We have one that's just to the right of the vertical asymptote x equals -3. And we also have one that's just to the left of the vertical asymptote x equals to 2. So we have 1, 2, 3, 4 invariant points here. Let's find the x values of those points, and then we can plot that information for our reciprocal function. So we have when y equals to 1, there's 2 points, and when y equals -1, there's 2 points, and our reciprocal function would have the same y values for those points. So let's find the x values. We can use our graphing calculator to help us find the intersection points, which would be the points where y is equal to 1 and where y is equal to -1. So we graph both functions, and then we do the intersection, second trace, number 5. I want to be close to one of my points, hit enter, jump to the other graph, close to one of my points, hit enter again. Okay, the calculator I have on the iPad for some reason does this every time I try to find the intersection points that involve reciprocal functions. So I'm on my Casio here. We're just going to get rid of this. It should work fine on your TI, hopefully. On my Casio, I've entered both functions into the graph, and I'm finding the intersection points of the two functions. And it tells me that when one of the points when y is equal to 1 is x is equal to negative 3.19, we'll round it to. The other point when y is equal to 1, x is equal to 2.19. And then when y is equal to negative 1, x is negative 2.79. And also x is positive 1.79. So really we already have those points plotted. We just find on our original function, the graph of our original function, where is the y value equal to 1 and negative 1. So I'm going to draw the middle portion of my reciprocal function graph. I'm going to join all those points together, and it's just going to continue down, and then same with this left side, join all my points together, and it continues down. I'm actually going to go over it with a brighter color because it's just hard to see. Okay, so looks something like this. Now for the two outside points. Really, all I need to know is where they intersect. That would be good enough information. I know it's going to get really close to the vertical asymptote. It's going to go through that invariant point, and then it's going to curve and get really close to the horizontal asymptote. That's good enough information. On the right side, it's going to get really close to the vertical asymptote. It's going to go through our invariant point, and it's going to get really close to our horizontal asymptotes. Okay, so label any intersection points 2.19 and y equals positive 1. This one down here is x equals 1.79, y is negative 1. This one over here is x equals negative 2.79 and y equals negative 1. And this one is x equals to negative 3.19 and y equals positive 1. So those four are our invariant points, and then the pink color, the three curves, make up the graph of the reciprocal function. State the non-permissible values of the reciprocal for x. So we already did that up here. X equals negative 3 and x equals 2. NPVs, x equals negative 3 and x equals 2. State the equations for any vertical or horizontal asymptotes. Our vertical asymptotes are the same as the NPVs, so x equals negative 3 and x equals 2. Our horizontal asymptote is y equals 0 for all reciprocal functions in Math 20-1. Given the graph of a reciprocal function on page 402, your turn, find the equation of the original function. So I've already drawn what the graph looks like that we're given. It looks like this with our two curves. And where did we see two curves like this? What kind of reciprocal function was that? That was when we had the reciprocal of a linear. Because remember, the reciprocal of a quadratic looks quite different as we saw in this example here. So we should expect that our function f of x will be a linear function, and we're given a point that is on this reciprocal function. We also can see that our vertical asymptote is at x equals -1. That tells us that x equals -1 is an NPV for 1 over f of x, which also means x equals -1 is an x-intercept for the function f of x. Then we can write our function f of x equals a times x plus 1. Because if x minus 1 is the x-intercept, then the factor x plus 1 must be in our linear function. So how do we solve for the a value? Well, we've been given a point here that's on the reciprocal function. And if we have a point that's on the reciprocal function, we can figure out what that point would be on the regular function. We have x, f of x, and 1 over f of x. X is -2, and 1 over f of x is -1 over 4. The reciprocal of -1 over 4 is -4. Then if we know that the point -2, -4 is on f of x, we can sub that point into our function. F of x is the y value, -4 equals a times the x value is -2 plus 1, and we can solve for a. -4 equals a times -2 plus 1 is -1. Divide by -1. We get 4 is equal to a. Therefore, our function f of x would be 4 times x plus 1, or f of x equals 4x plus 4. And it doesn't say to draw the original function, but we can draw it on our graph. We have a y-intercept at 4 and a slope of 4 over 1. Y-intercept at 4, slope is 4 over 1, so up 4, 1, 2, 3, 4 over 1, down 4, 1, 2, 3, 4, left 1, down 4, left 1, down 4, left 1, and then join those points with a line. And then we can look at, does it look like the two graphs intersect at our invariant points, which is when y is equal to 1 and when y is equal to -1? Yes, it does. So we can tell from our graph that our function f of x equals 4x plus 1 seems correct because our invariant points are in the locations that they should be, which is when y is equal to +1 and y is equal to -1. That brings us to the end of lesson 7.4, which is also the end of chapter 6 and 7.4 notes.